Morning, mathematicians.
Hey, good morning.
Well, how did the what did we do yesterday? Oh yeah, linear. How did the evening of linear solving linears go? Everybody full of happiness? You're always welcome to start class by asking me any of those kinds of questions you want, and I will answer as I can.
I've only watched the first hour of yesterday's recording and my head hurts. So I'll try to finish that before I ask anything.
Well said, yeah. Yeah, that was a rough day to kind of not take in live.
I think actually, Evel and I had a question about the last one, number 30, of the linear homework.
Okay.
Because we tried, checking it, with GeoGebra and Desmos. And we weren't sure if we were right or if it would just be the graph being weird because of the lines. If we were wrong or if we were right because of the
Yeah.
how the program works with straight lines. But
I made a little progress after class on something with that yesterday, but you're more than welcome to say even simple questions like, hey, this is the answer we got. Is it right? I'll answer that question.
Okay.
And, if it's
let's
not,
see then.
I'm looking at my, you said number 30, right?
Yeah, number 30. I gotta find where we had it. Let's see. I think that was the last one for the last section, right?
Yeah, that's right. It's 2.3, number 30.
Yeah, here we go. Okay, so we got well, A, obviously they gave you the answer, so that worked out. But then for B, we got y equals the cube root of and then in parentheses x minus 1 plus c times e to the negative 6x power, close parentheses, over 2. And that's all under the cube root.
X minus
I could write it out.
No, I got it. I wrote it a little differently. That's really close. If it's not exactly right, I just wrote it a little differently. I didn't have any.
Yeah,
I didn't have y equals cube root. I just had y cubed equals, and then I had sort of 3 plus signs or plus and minus.
Yeah. I had it that way, but right before, so.
I got a different number, I think.
Go for
I got
it.
y cubed. I got y cubed equals 1/2 x minus 1/12 plus c negative 6x.
That's what I wrote down.
Oh, 1/12. Why did I not get that?
The 1/12 appears as you integrate the 3x e to the 6x by parts.
3x e to the 6x. Yeah, so I got.
Yeah, because you have the integral of e to the 6x is not just e to the 6x.
Mm-hmm. Yeah, because e to the 6x times 1/6. So right. So okay, I get that. Yeah. So I see I did that wrong. So yeah, once you integrate by parts in the integral, you actually have probably, so I think I see that. And that's
right. Somehow there's like a 1/2 that gets multiplied by a 1/6 as you integrate.
Yeah. Okay. I see that now, I think. Okay.
Yeah, because the integral of e to the 6x is e to the 6x, but then you got to divide by 6.
Okay.
It's literally like 3 steps back.
Probably explains it. Yeah.
So, for everybody else, that goes for y'all too. Anytime you want to either right before class or right after to, just ask if you got some question right, or, after is better only because you might have we might need to look at it together a little bit, and we can always share. I can share a whiteboard that you can write on. We all look like first graders when we write on it, but I was doing that with Raymond after class think it was yesterday. Just
Yep.
checking something out. And it's like, if you send me a text, I've given you guys my cell phone. If you send me a text and we hop on there for 5 minutes and write on a whiteboard together and stuff, like that's super good. So I'm not setting particular office hours for that reason, but I hope you'll take me up on that as necessary. I'm wading through your homework. I think I'm through half of them, and I want to finish that today. But when I see questions in there, I always think, man, I hope they got that, cleared up. I'm posting my solutions, and so sometimes you looking at me and my solutions will make it cleared up, despite whatever you might have sent, and so forth. But point is, get your questions answered. Okay. So this is our last section before the first midterm, and we are looking at something I showed you an example of the other day, and it's one of the cool applications of differential equations, and it helps you understand how you would write your own equations, or a place where you would. And fortunately, the solving of them is not terrible. Most of these problems are not as awful as, well, some of the examples we did yesterday solving linear equations. But we'll probably use that technique to solve some of these. But again, the classic example of a compartment analysis problem, and I'll start with what I consider to be the...
Hey, Doug, quick question.
Yeah, go ahead.
What is the nature of our test going to be? Is that, are you gonna like upload a PDF and then we...
Yes, I'm gonna upload a PDF, and I'm gonna give it to you on that day, which I think this week is Thursday, and I'm just gonna give you the whole day to do it. I don't mean you get 8 hours to do it, but I'm gonna let you either take it in the morning at normal class time, or take it, in the afternoon. But you're gonna have roughly 2.5 hours, and
Okay.
then you're just gonna scan it and send it back to me, just like you did your homework.
Okay. I imagine it'll be pretty straightforward.
Yeah, it is. I'm not a hard tester. You're definitely going to be
I
prepared.
just wanted to ask because
Yeah.
it's soon.
And tomorrow we're gonna do a little bit of review, a little bit of spend time on introducing our first project, and so we'll have a chance to talk about that. I do have, if you want to get a head start, I do have a review for that test already posted in my open math, and all of them are already in there, so you can actually start messing with that stuff, or on the earlier side if you're that type of person. But those reviews, I would say, are essential, both because it's me telling you what things I think are important that you really need to understand, but also I'm giving you practice on those things as well. So those are really essential. Okay, so I drew this picture for you the other day. Whoops, that's not what I want to do. And I want to do it again. I got rid of everything. So the idea is you have a compartment, and so, one example of this would be something, kind of a liquid tank. You've seen maybe these at factories, just driving down the road or something, but some huge tank out there. Could be a lake. The compartment could be a lake, could be just the room that you're in, and the air that happens to be in that room. Basically, it's any kind of location that has something flowing in and something flowing out. It doesn't have to be liquid, could be air, all kinds of things. But really the concept is this, and this is no different. All you really have access to is just kind of the rate of change of something. So if, for instance, and let's just do this via another example, but let's say you have 12, and I'm going to use a little bit more kind of normal language for this. Gallons per minute is a common flow rate. And notice I said gallons per minute, and that's often written as GPM, but it really means gallons over minutes, right? And so for us, it'd be easier to write it as gallons, 12 gallons per 1 minute. But it's usually written GPM. And so that's kind of just the amount of, we'll say, as I did the other day, just kind of the liquid that's actually coming in. But let's say that it is also 0.4 ounces per gallon in some chemical that's coming in. I don't know, let's say iodine. I don't know what iodine does. So a percentage of that liquid is iodine. And of course, your goal in, and you're doing this consciously. In other words, your goal in putting that in the tank is to either dilute it or increase its chemical composition based on what's in there. And the most practical or the most typical example of this kind of problem is where the amount that's coming out is also 12 gallons per minute. In other words, you're equalizing how much liquid is in the tank. It's not getting any fuller or any emptier, although we'll play around with what that looks like too, just for the fun of it. Let's say this is a 500-gallon tank. And let's say that the iodine level at time 0 is 0.1 ounces per gallon. And so notice in this case, it's pretty obvious, since you're putting in 0.4 ounces per gallon, that you're actually increasing it. And I guess you might say that'd be the common thing to do. In other words, you look inside the tank. I mean, again, probably a pool is a good example. You know, when you say, okay, well, there's not enough chlorine in that pool, so let's get some more in there, you know, so you add something to it. So we're obviously increasing the concentration, because right now it's 0.1 ounces and we're sticking in 0.4. And so, of course, the question is to kind of come up with a model. So if and I think this is an important way to kick all of these problems off, because it's very confusing as to whether you're thinking about the rate of liquid or the rate of change of iodine. And so we're going to let I be equal to the number of ounces of iodine. In other words, we don't care about the liquid. That's the whole point here.
Is this always the case where we're going to let our function be equal to the amount of substance?
That, I want to say yes to that. I mean, my gut reaction is to say yes. Maybe we'll run into it, but very typically 90% of the time, at least, if not all the time, yes is the answer to that, because that's kind of what you're interested in. Liquid is just the delivery system, if you will. And so you're
Right.
concerned about just one element of it and so forth. So yeah, often that's the case. And of course, I could just say you're adding 0.4 ounces per gallon, you know, like as a powder. It's not like it has to be coming in as a liquid. Does that make sense? So
So I is in ounces per gallon. Is that not a concentration?
yeah, so it's really it's a concentration in this case. And I'm saying that because over here, this is, so I could be, yeah, and that's one of the questions. And I actually was kind of thinking in my own mind about this while I was even writing that down. Like, should I leave this off? Should I say just a number of ounces? Or should I make it ounces per gallon? I mean, it's kind of up to me, actually. I'm not really sure. Why don't we start just saying it's the number of ounces and not think of it as a concentration? Let's just see where that goes.
Right, because you could divide by volume and then find the concentration.
Correct. You can always turn that into a concentration if you want to. So again, your goal in doing this might be because you have your 500-gallon tank and you want 30 ounces of iodine in it for whatever reason. That's what you want. And so you say, oh, I don't have that much. And so then I'll put more in or whatever. Or you could say, I don't really care how much is in the tank as an amount. I care how much is a concentration. In other words, I want it to be 3% iodine, because that's what I want coming out the other end. That's going to be a healthy pool, or, whatever the case may be. So yeah, it's kind of a question of, am I interested in this as a concentration or just a set amount? And it is easier to think of it as an amount. So maybe let's start with that. Let's just leave it as ounces of iodine. So again, just to highlight that, not liquid. And so in the end, this is kind of the backbone of all of these types of equations. you basically realize that since the tank is changing, that's kind of the whole point. And again, the cool thing in life is that many things are like this. And when I teach calculus, I always kind of like to point out calculus is the mathematics of change. And so if something is changing, then you better understand calculus, or you're not going to be able to model it. So as I mentioned the other day when I introduced a problem like this, it's kind of like a lake. Well, if you have a river flowing into a lake, then it's bringing some element of chemistry from the hills into that lake. Therefore, the lake is changing. And so your ability to kind of understand what's happening in that is really kind of a key. And so again, this doesn't have to be controlled like this problem is. It could just be natural. So the same is kind of true for the air we breathe in our world. We burn things in factories and so forth. And so we're introducing chemicals into the air. And so, what's actually in the air is changing. And maybe you've heard, especially in light of our area with smoke and so forth, and one of the ways air quality is measured is in parts per million. So it'll be like, so many parts per million of something, but there's just like so many different chemicals that could be in the air. And if you're near a factory, then maybe be concerned about that particular chemical. And of course, scientists would be explaining how, a certain level of parts per million is okay because air, all of our air has some sort of negative chemical in it, at least in a tiny concentration, but that doesn't hurt us. But then when it gets over to a certain amount, then all of a sudden it hurts us. And so then we start paying attention to, the compartment of air that's, say, in the Rogue Valley, and what's in it. Maybe it's a chemical, or maybe it's just smoke. So again, what I'm interested in this explanation is just that you see this a little larger than kind of the book problems that any room, whatever you want to call that room, a valley or a lake or a tank or whatever, even the blood in your bloodstream. I was actually trying to make up a problem that involved blood alcohol content before class. I'm not sure if we'll take a stab at that or not, but it's like, that's really interesting, right? Because I introduce alcohol to my bloodstream, and then my tank of blood, which is like 5 liters, is now got a concentration of some other chemical coming in, and then of course your liver is filtering it back out the other side. And so this is just a really prevalent application. It's, in a sense, you might say, one of the reasons why this mathematics was invented. And so anyway, what's the fundamental equation? And so you look at the iodine and you say, well, you really say this, and that's kind of the whole concept here. Hey, good news, bad news. I don't know which way you look at this, but the amount of iodine in the tank is changing over time. That's kind of the problem. And so the mathematician does not have to wait until you've dumped a bunch of stuff in and then go test it to see how much is in it. We can actually predict it. And of course, that's the whole point, to control this, to turn on the pump of 12 gallons per minute into the tank and leave it on for the correct amount of time to get it where you want to get it. So let's see. So let's just make a note about this. Notice if it's point, and unit analysis is a really interesting part of all this, but if it's 0.1 ounces per gallon, and I multiply that by 500 gallons, which by definition is over 1, then notice the gallons cancel and I get 50 ounces. So notice I gave you a concentration. I said I have 0 equals 0.1 ounces per gallon, but I could have just as easily told you, notice it looks like 50Z, but I could have just as easily told you that there were 50 ounces in the tank. Does that make sense? That would have been another, well, what do we call this? We call this the initial condition.
I think you're gonna have to turn I back to ounces per gallon.
Yeah, I like how you're thinking. So let's say that the whole reason you did this is because you just looked at your tank, because this is, this is at a business and you're trying to, make sure it stays at the right concentration and so forth. Let's just say that your goal, again, just to make it interesting and to give you time to think, let's just say your goal is to have, say 100 and, I don't know, let's say 120 ounces. So we'll just kind of leave that in the back of our mind. Look, the whole reason you turned this on is because you realized, oh, there's only 50 ounces in the tank, and you really know you need 120. And so then you turn the pump on and pump higher concentration iodine in there. But the goal is to like turn the pump off, don't just keep going indefinitely, but to kind of turn it off at 120 ounces. And so the problem is as soon as you turn it on, the concentration's increasing. And that's, if you will, the advantage of me giving this to you as a concentration, 0.1 ounces per gallon, but then I pump in 0.4. So I'm increasing the concentration. So the problem is it's changing all the time. And so how am I supposed to keep track of it since the iodine over here is changing constantly? And so all of these can be solved by really recognizing that you have a rate going in and you have a rate going out. And the rate going in was effectively a positive and the rate going out is a negative. And so that's the backbone of all these types of equations. The rate of change would be the rate in minus the rate out. And so we got to come up with expressions for those. And again, when I say rate in, I'm not talking about rate of liquid, I'm talking about rate of iodine. So what's the rate of iodine going in? Well, let's tackle that. Well, I have 12 gallons per minute. And I have 4.4 ounces per gallon of iodine. And so notice the gallons cancel and you end up with 12 times 0.4, which is 48 or 4.8. You have 4.8 ounces per minute. Notice that's a rate of iodine. So the key is, if this is an equation, every one of the units here, di dt, has to also be ounces per minute, because this is an equation. And rate in is ounces per minute, and rate out is ounces per minute. So notice you have a constant rate going in. Notice there's no variable associated with that. But the rate out is much harder. Because does it make sense? It comes in, and again, as I mentioned the other day, we're going to assume it mixes completely. If iodine was really heavy in the picture that I drew, for instance, it could effectively, come in, drop to the bottom of the tank and go out while this liquid over here never even mixes with it. Does that make sense? Or we're just going to assume we're stirring it. So it ends up uniform. And of course you might have to do that actually as a part of your system. But the problem is you do have 12 ounces or 12 gallons per minute going out, just like you did in the rate in example. But does it make sense? This part is much harder.
Well, we have a little inconsistency with our units, so it's difficult to tell. So is I ounces per gallon, or is it just ounces?
Let's start with ounces and we'll change it if we need to. I see what you're saying, because you're saying over here, I said ounces per gallon.
So in that case, we would take I and divide it by 500 gallons, because that would be the ounces per concentration in the whole tank.
Yeah, that's exactly correct, because I'll add this to the statement over here. And David is right, saying ounces here and then not using ounces in the, the original amount over here, giving it as a concentration in that element is a little bit confusing. I'll leave it alone for now. But the problem is the amount of ounces in the tank is actually changing. And so That's kind of the key to this, because really the amount of ounces in the tank is I. There's I ounces in the tank. That's the whole point of this. That's what's so complicated. It's changing. Now it started at 50, but you can't say it's 50 because as liquid pours into the tank, it's going 50, 51, 52, 53. That's going up all the time. But what doesn't change is, well, how many gallons are in the tank? And so that is going to be 500. So the concentration going in was 4.4 ounces in every single gallon, whereas the concentration going out is I ounces in a total of 500 gallons. But notice that produces the same exact unit. In other words, we have ounces per minute going out. Let's see, can I do that in my head? 12 divided by 500, that'd be the same as, can you do this kind of stuff? Do you have to have a calculator to turn that in? I'd like to write this as a decimal, but 12 over 500 is the same as 24 over
Can't hear
1,000.
you anymore, Doug. You froze.
Uh-oh. Not from my end. Can you hear me okay now? Oh, you guys froze.
You're muted, Doug.
I'll see you guys freeze and then I'll know to shut up. And anyway, whatever. Let me get my screen shared and we'll get after it again. So in terms of being able to solve these problems, this fundamental equation right here is really kind of the key. And in terms of whatever complexities arise, it's just very important to understand that, to pay attention to the fact that those units all need to be the same. I mean, in the same way, if I say what's 5 meters plus 10 inches, you can't say 15. The same thing is true here. For these things to be equal, all these units have to be the same. So anyway, as I started to say, if I wanted to turn 12 over 500 into a decimal, you could just bust your calculator out, but 1200 over 500, 12 over 500 is the same as 24 over 1,000. Oh, now that's a decimal, 24 thousandths. So this is 0.024I, and also I don't really need to write this necessarily, but just to make sure you're seeing it, ounces per minute. And so there's my differential equation. The only access I had, because this is an example of a place where all there is change. And if you can't deal with change, if you can't write down, if you can't do math where change is involved, then you're not really going to be able to make any sense of a problem like this. So I can only describe how things are changing. And so this is our differential equation. So di dt equals 4.8 minus 0.024I. And I can get rid of all the units now. So I need the part above to kind of make sense of that. And so we just wrote a differential equation. That's the only access you have to this problem. Now, of course, your job is to, because in the end, all somebody really wanted to know is how to turn this thing off when there's 120 ounces of iodine in it. But of course, what we'd really like to produce from this to allow us to answer that question is kind of an I as a function of T equation. That way I can use it to answer the questions I might want to answer. So you should look at that equation and say, okay, cool. Now, what I'd like you to do is to try to solve that. Even though this is an interesting problem because this is separable, you could actually get the i's on one side and the t's on the other with this problem. You could solve this as a separable differential equation. And you could also solve it as a linear differential equation. So why don't you solve it as a linear? Maybe I'll quickly solve it as a separable. It's really unusual to find an example that has both options, but given that we just talked about it yesterday, solve this as a linear differential equation. And again, I'm just going to give you enough time to get a head start. hopefully you recognized you've got to get all of the I prime and I terms over onto the left. And now you're thinking, I would like that left-hand side. I'd like to modify that left-hand side to look like the product rule has just been taken of a derivative. We said yesterday that that isn't true right now, but it could be found to be true by multiplying both sides by this multiplier mu. And we said yesterday that that is e to the integral of whatever term is here, whatever equation is there. We got lucky here, remember, because there was no equation in front of this. Great, there needed not to be, but there wasn't here. And then notice this equation isn't even a function of time. It's a really simple equation. It's just a constant. So I'm really just taking the integral of, well, the number 0.024 with respect to t. And so you say, oh, well, that's easy. The integral of a constant just adds a t to it. And so there's your multiplier, 0.024 t. So that was our technique. And so then I say, great, now I got to multiply that by both sides. So I have e to the 0.024 t multiplied by di dt. I have e to the 0.024 t multiplied by the I. And I have e to the 0.024 t multiplied by the constant 4.0 on the other side. And again, from yesterday, I hope you can stare at this and go, cool, that's amazing. That really worked. I can see that this expression right here, if I take its derivative, if I take the derivative, there it is. And you might have been able to say in hindsight, oh, that's kind of, I could have guessed that one actually. If you think about it, I could have guessed the multiplier here. But we saw lots of examples yesterday. It was way too hard to guess. But it's like, yeah, sure enough, the derivative of e to the junk is e to the junk times the derivative of the junk. Well, the derivative of 0.024 t, of course, is 0.024. So look at that. There it is sitting out in front. So this really is sitting here as the power rule, which means we now have the luxury of rewriting this as e to the 0.024 t times I. Remember, those are the non-derivative components of that. And so, as we said yesterday, we're used to the power rule. When you take a derivative of junk times junk, we're used to the power rule taking us this direction. We're used to going from two things multiplied. We're going to take its derivative. We're going to end up with this power rule expression. But in our case, kind of fun, we're actually going the reverse. We're undoing the power rule. So that's the genius of this idea. You've got to make that expression look like the power rule. Since it had both the I and its derivative in the problem, some smart person thought, hey, that's kind of cool. I wonder if we could get that to look like the power rule. And of course, all we did is rewrite that left side, and the right side is unchanged. Now we do what we always must do to solve a differential equation, which is to get rid of the derivative. If my goal, I said this yesterday, and I just want to keep repeating this so that it goes deeply into your brain. If my goal is to find I as a function of t so that I have a model for the iodine over time, I don't want any derivatives in it. So I'm going to have to integrate to get rid of them. So the cool thing is if I integrate the left side, it just means that the derivative disappears. Wow, I was going to have to take the derivative of a problem that involved a power rule, but since the fundamental theorem of calculus says an integral and a derivative are inverse operations, then hey, I don't have to do it. And again, you should see the brilliance of this, because the whole time I was trying to solve for I, not I prime. The original problem had I prime in it. And now I don't have any I primes anymore. I just have I. So all I'm going to have to do is divide by that and I'll be done. But I do have to take the integral of the other side. And let's be a little careful here. You might be able to do this kind of in your head, but let's let u be equal to 0.024t. And that would mean that du, the derivative of both sides, is equal to the derivative of 0.024t. Well, the derivative of 0.024t is just 0.024. But thinking of this in terms of improper integrals, the derivative of t also has to be noted here, because I'm taking the derivative with respect to, well, I don't know what. So the derivative of u is the derivative of u. It's not 1. The derivative of t is the derivative of t. It's not 1. So if I integrate this right side with respect to t, then I've got a new problem now. I've got 4.8 times e just to the u power. But since I switched to u, that means I need this to be a du, not a dt. Well, what is dt equal to? Don't I have to divide that 0.024 to the other side? So again, maybe you're good enough at integrals, you didn't even need to make that substitution. But notice the integral of e to the junk is e to the junk, but as a shortcut, you have to divide by the junk because we're taking the derivative of the junk. So you don't still have to write that substitution down, but you need to understand it. So let's see. Since I'm working with decimals, I might as well take 4.8 and divide by 0.024. And when I do that, I get exactly 200. That's kind of interesting. I wonder why that is. So of course, the beauty of that is the integral of e to the u is e to the u. And 4.8 divided by 0.024 is 200, and so I'm basically done. And then I just need to replace u with what u always was. I never really wanted that as part of this problem, so replace that u with 0.024t. And then all I have to do is divide by both sides by, notice what you get. This is kind of interesting. 200 e to the 0.024t, but then that gets divided by e to the 0.024t. But then you also have this c, which also gets divided by 0.024t. So your final function for this then, since those just cancel, notice if you forgot the c, then you would just say I is 200, which means it's a constant. It means like you're pouring stuff in and it's just always 200. That's how important the c value is if you don't get this right. Notice I just chose to move the e to the top, changing its exponent. And so now I have a model. Now I want you to think for a second about this model. What happens to this if you just like turn the pump on 12 gallons a minute into this tank? If you turn this pump on up here and you just like forgot to turn it off, you came back like a month later or whatever. What's the limit of this sequence? This is the way a mathematician would say this. So you should understand this language now. What is the limit of I as t goes to infinity?
200.
Notice if t goes to infinity, maybe it's a little easier to see down here, but you'd end up with e to the infinity, c over e to the infinity. Well, that's a big number. C over a billion, that's on its way to 0. And so that just leaves 200. Why does that not surprise you? Why would it be 200? Look back at the original problem.
At some point you have the same concentration flowing out. And so you still have water flowing out. It's just reached the maximum concentration.
Yeah. Does it make sense that the concentration inside this tank is going to be 0.4 ounces per gallon? If you let this run long enough, it started at 0.1 ounces per gallon, but if you just let that new liquid flow into it, eventually that's what the tank is going to turn into. It's also going to be 0.4 ounces per gallon. Well, notice what happens. If you take 0.4 ounces per gallon times 500 gallons, that's 200 ounces of iodine. So in a sense, you could say, well, it's a good thing that 200 showed up there because that's what's going to happen over time. So it's a small wonder that 200 showed up. So that's just kind of cool to notice, isn't it? Now, our problem, though, we just said out of interest, we wanted to shut this thing off when it got to 120. So now we understand, oh, well, don't leave it on too long then. So you could actually blow past it. So it started with 50. It's on its way to 200. We need to shut it off at 120. And of course, that's the whole goal, because now that you have this equation right here, you kind of own the relationship. Well, I guess you own it if we consider our initial condition, right? Notice that actually didn't matter what the initial condition was. Notice we never figured out C, and yet we were able to answer this. Does the initial condition matter if you just turn the tank on and then pour in stuff forever? Does it make sense? It wouldn't make any difference if it started out like solid iodine, this would dilute it, or if it started out pure water, this would increase it. It's going to go to 200 no matter how much you started with. Isn't that interesting? The C didn't have a hand in it. But we noted, as far as initial conditions, that I of 0 was equal to 50. And again, this is where what I said at the start is a little bit confusing, and why I should have said, since I was, this is what David pointed out earlier, but really this was my initial condition, since I was defined as ounces. My initial condition was I had 50 ounces in there, not 0.1 ounces per gallon. So if I stick that initial condition in there, in other words, at time 0, then I'm going to be able to figure out what my C value is. And so if I is 50, when T is 0, notice you end up with E to the 0, which is 1. So the only way 200 plus C is going to be 50 is if C is equal to negative 150. So that means our model, not all models, but our particular model is slightly different. And now we can answer the question we want to know. So as I like to say, we own the relationship now. This is what algebra is really about, is the fact that in life there are numerically quantified relationships. And so, of course, there'd be a relationship to how much iodine is in the tank over time. And now we own that relationship, not that relationship. We own it. So now we can figure out anything we'd want to know. So the kinds of questions that I could ask, as I will on a test, would be, okay, great. So you leave that pump on for, say, 25 minutes, how much iodine will be in the tank? Or the question I asked, which is, if I is, and I guess I kind of like the question I asked. Just because I think it's more realistic. You're not just going to turn the tank on randomly for 25 minutes and then just kind of wonder what happened. You're turning it on for a reason, and you want there to be a certain amount of iodine, 120, and so solve for T. And then of course it's kind of fun just because you guys have studied a whole bunch of math over the course of your lives, and this isn't an easy equation to solve for T. Involves logarithms and so forth.
Hey, Doug.
Yep.
So if the question was to find like when the tank is going to reach a certain concentration, would we solve the iodine equation? So we would take the concentration and like multiply by the whatever the volume unit is, and then that would give us the amount of iodine, and then we would solve the equation for the time for that amount.
Yeah, if it was a concentration, then let's see. Yeah, that's exactly right. So if I said I wanted to be like 22% iodine, then you'd have to take, I'm gonna erase this, but you'd have to take 22% times the 500 gallons in the tank, and then that would give you the 120 or whatever. You know, in this case, it would give you the actual amount. That's a good question.
Right. There was a question in
Mhm.
the homework that I should
Yeah.
probably reread and ask you about tomorrow, but that had to do with something like that. And so I got confused about the units.
That's correct. And so that's part of the reason I left this a little ambiguous, going back and forth between an amount and a concentration, because they are kind of two ways of saying the same thing, but that can easily trip you up. And you can also understand why people would look at it this way. And you should understand that the only reason a person might even pick 120 here is because as a, you know, as a percentage, 120 divided by 500 is 24%. So I could have said, turn the tank off when it's at 24% iodine. And that would have been the same exact math, but that would have, you know, made it a little more confusing.
Yeah. And my confusion is why I won't shut up about it.
I'm glad you are. One of the tips I gave you on my syllabus that you likely didn't read, at least I wouldn't have if I was you, was to look at the problems that are being assigned and even try to do them before we talk, because then you've gotten stuck. And then you're, you know, what I'm saying is answering questions for you. You're getting more out of class because you have questions, if you will, than just listening to me talk, and hope for the best. So all kinds of simple algebra mistakes you could make. You might agree it's extremely tempting here to go 200 minus 150, but not only should you not do that, you should have reasons why you should not do that algebraically. But in my case, I'm going to subtract 200, which gives me negative 80, and then I'm going to divide by negative 150. So I end up with 80 over 150, which I guess is 8 over 15. And it's getting close to getting logarithms involved. Yeah, it looks like I'm now getting logarithms involved. And so you can't solve for a letter in the exponent without a logarithm. So if I take the natural log, I'm taking the natural log of both sides. I don't care. Like most of you would have turned this into decimals, and I have no problem with that. I just don't happen to be staring at my calculator. So whatever the natural log of 8/15 is, if I divide by negative 0.024, I will have the time. And then we're going to go check our work and kind of see if this all lines up. I got 26.2. T is approximately 26.2. And notice I haven't been paying much attention to time or like how it was measured, but our time has been minutes, gallons per minute, and so forth. So this is actually 26 minutes. So that's kind of cool. I mean, in the end, all you really wanted to do is have 120 ounces of iodine in the tank, and you just wanted to make that happen. Keep in mind, math doesn't, I mean, the real world doesn't always have to be complicated. If you establish that there's 50 ounces of iodine in the tank and you wanted 120, then couldn't you just dump 70 ounces of iodine into the tank if it was a powder? Like, there isn't necessarily saying, there isn't necessarily, you know, you don't always have to make things complicated. In this case, it's, if you will, because of the delivery system. So if your only question or your only goal was to get 120 in there, you know, then maybe you don't have to go to all this trouble. But keep in mind, what we have is a model that tells you how much at any given time. And so that's what's kind of fun about this. Now, toward the end, to the end of checking our work, let's go play a little bit with this and just kind of visualize and help it maybe soak in a little bit. So I'm going to share this screen. Are you seeing slope field plotter now?
Yep.
Good. I think I'm getting better at this. So notice I typed in the differential equation that we got. dy dx equals 4.8 minus 0.024y. Well, notice because this problem had i's and t's in it, you got to think a little bit harder. Like when I got right here and I started putting in the 0.024, I was thinking, let's see, do I put y or x there? Like I could have screwed that up. Well, again, this is why the dependent and independent variable are so important. It was di dt. So time was the independent variable and I was the dependent variable. And so this was an I, and on top of this was dy dx. And so I knew that needed to be a y. That'd be easy to screw up. Awesome. So now I hit graph. And let's see. And notice I have a chunk on here, but let's think about this. What size window do you need in order to be able to see this? And again, I'm not looking for something random. Like I want you to really think about this. What is the meaning of y here? For us, that was I. What is the meaning of t? For us, that was, or x, that was time. And so what's the range and domain? This is what range and domain really mean in the real world. So for x, well, x was time. And so what times make sense? What should I be putting here for reasonable times for a time minimum and a time maximum? Well, we went out to 26 minutes to get where we were going, but I may even want to go past that. So I don't know, I'm going to put 40. I have no good reason for 40. I'm going to leave a little bit negative in there just so I can see the left side of the graph, but I could say from 0 to 40, 0 to 50, 0 to 80. I could even stop at 27 or whatever. But I just want to see the graph. And so that was the times. Well, what was the amounts of iodine? Well, it started at 50. And then we saw it worked its way all the way up, well, potentially clear to 200, right? So it's kind of like 0 to 200 or something. So again, I think I'll leave -5 and I'm going to put 200 in here. So notice I've really got to control this. So there's my graph. And now notice this is a good place for kind of density. And notice it's kind of ugly that it's not square. See how it's like tall and thin? I'm not really liking that too much. So I'm going to add more to our time. Like maybe I'll make it 200 as well, just so it looks square. I guess one of the things I'm curious about here is there something about the shape that you see here that you're not surprised by? Ultimately, I want the answer to that to be yes, but maybe it isn't yes right now. What's not surprising about that?
That it approaches that limit of 200.
Yeah, notice every single case you're in, as the language I've been using earlier is like it wants to exit the stage at 200. Do you see how it's on its way there? Now notice 200 minutes was not enough to get it there. 200 minutes was not enough to make it reach that point. So again, I could take this out further if I wanted to, past 200 minutes. But notice if you started with less than 200 ounces of iodine, then it's going to work its way up to that. So we started at 50, so it's going to work its way up. And of course, it's kind of cool that I can go in here and type at time 0, we had 50. And so this is our model, right? Now, the other thing that's really cool is, do you understand that we did not have to do all this math to get the answer to our original question? If your only goal here was just to turn the thing off at 120, does it make sense you could answer this from this graph? You don't need to make an equation or solve it. In the real world, when people don't have to do math, they're not going to do it, both because it's time consuming, hard, and because you might screw up. And so, you should have enough math in you to kind of think it's cool to be able to do it on my own and not need technology. Let's see, I don't think there's any easy way I can do this, but can we at least verify that our answer of 26 is right based on this picture right here? Just at least roughly 26 minutes. So there's 20, there's 40. So halfway between would be 30. So it's like right about here. And then if I go up there, look at that, 120. So it looks reasonable. I wouldn't be able to get 26.3 minutes. And so if, if a math teacher was trying to make an argument, yes, you do need math. You wouldn't be able to get 26.3, but you can at least say, well, there's 120 and what does this hit at? And, I can see about what the answer to that is. And if the application in the real world doesn't call for perfection, it doesn't have to be exactly 120, then good enough, close enough. That's kind of cool. Let me ask you another question. What if I take the Y max up and I'll take them both up? Well, maybe I'll just start with that. To keep it square, I think maybe I will take the time out to 400 minutes. What do you notice about the top part of this graph that doesn't surprise you? And what does that mean?
That's in the scenario where we had too much iodine and it's going to dilute it down to 200.
Couldn't be said any better than that. So we said it was on its way to 200, but what if the tank started more than that? Does it have to start less than 200? No, it could be too concentrated. And so in the end, you're diluting the tank. But notice what's kind of cool about this is in every case, doesn't matter where they kind of started from, they're on their way to 200. And notice I took the time out enough that you can actually see them all making it there. Like 400 minutes is enough that it's almost indistinguishable. Are they perfectly 200? No. Mathematically, they're never going to get perfectly to 200, but they're practically there. I don't know. What do you think after 300 minutes? Practically, it's pretty close after 300 minutes, just looking at the graph. So that's kind of cool. Again, that's why there's a family of solutions here, because no matter what, this is going to be on its way to 200 thanks to what's coming inside the tank. And so there's all these individual solutions that might be the case depending on what you started with, but they're all going to exit the stage at 200. And so that should kind of make sense. That's kind of cool, I think. I won't take the time to go to Desmos here, but if your equation solving skills got rusty over time, like you're probably fresh enough that when we just solved it for 26.2 minutes, you thought, yeah, I can still do that. But does it make sense if you graphed your I as a function of T? Maybe I will do this really quick because it doesn't take that much time. And also I'm curious if what we did the other day still holds true here. Like if I say I as a function of T and then instead of Y's and X's, I want to leave the letters alone because it's kind of confusing to have to convert. So if I go over here and say, here's my equation, we said 200 minus 150 times E raised to the negative 0.024T. The question is, does it like that? You might look at it again and your first instinct might be like, hey, it didn't work. But again, when you look at domain and range, well, of course we don't see it because ours started at the point 0.050. And so I don't see 0.050. And then, then we back up and go, oh yeah, look, now it really does start at 0.050. This is another fun thing that's sort of irrelevant, but just in terms of your growing skills with Desmos, you can go in here and say, actually would like the time to be greater than 0. Notice you have to put brackets around that. And then you don't have to see the irrelevant negative part of this. And so, there's my model. And so if my goal was to figure out when I wonder if I have to say I of T or if I can just say I is 120. Notice it didn't like that and wanted to maybe I of T will work. I don't know. Yeah, it liked I of T. Notice I can go in here and cheat and get the answer. Like if you're bad at algebra, again, that's just kind of cool. If this is a $1 million process, as I mentioned, I had a friend that worked out at White City at a plant that, did this kind of chemistry all the time. And, these chemicals are not free. And so like, let's not screw this up. Well, we've just done a whole bunch of things to check our work. Does that make sense? And so now we can confidently, and that's why you get the big bucks. I mean, ultimately that's, for many of you, that's what you're doing in this class right now is you're going to be the person who's able to, answer these difficult questions. How do we fill this tank and get it to 120? Well, you now realize that's a pretty hard problem. And if you can not only kind of answer that, but even answer it with certainty, as I think we can now safely say that the answer is 26.22 minutes, checked it in all kinds of different ways, that's really powerful. So I like these problems because they're practical. I like practical stuff. But I also like them because I think they illustrate the big picture of everything we've been trying to talk about. So let's just do a couple of things really quick now. And then feel free again to interrupt with your own thoughts, as always. But I don't know if I'm right about this, but it feels like, just because we're trying to learn skills and so forth, could we I'll quickly solve this for you. Solve it as a separable differential equation. And other than just, well, that's kind of cool that we can do it two different ways. It's also, this isn't near as obvious. So I'm just going to go copy that thing wherever it was. Because it was right there. Because this is separable, but it is not near as obvious that it's separable. And in a sense, I should have copied a different version of this, because the version that we want it in is really this version. So I guess this is probably worth noting. Because your first reaction to this, and this is what I was talking with one of you outside of class yesterday. What's the deal with this? You might think your first instinct to this might be, oh yeah, I can get that 0.024i to the other side by adding it to the other side. But if you did that when you multiplied by dt, that 0.024i would get multiplied by dt as well. The only way you can actually separate this is to divide the entire thing, both sides, by 4.8 minus 0.024i. And multiply both sides by dt. That's what you'd have to do to separate it. Now you really do have all the i's on one side and all the, well, there aren't any t's, but all the i's on the same side with the i's, and there's nothing on the other side. And so now when you take the integral, and I won't belabor this point, but the integral of 1 over junk is the natural log of the junk. And the integral of 1 with respect to t would be t. What's missing though on the left side because of the chain rule? Is that the integral? The integral of 1 over junk is the natural log of the junk. If you take the derivative, to kind of check. Go ahead.
You got to do a u substitution.
Yeah, because really, you don't have to write this down, but you at least have to think about it. Really, you want to let u be equal to 4.8 minus 0.024i. Therefore, du would be equal to negative 0.024 di. And so when you get rid of di, notice you actually have to divide by, and that's what I missed, the negative 0.024. If I took now the derivative of this statement right here, I would indeed get 1 over 4.8 minus 0.024i. And so that's my answer right now. And so you might think, well, that doesn't really look like the equation we got before yet. But let's just play with this a little bit and see that that's actually the case. So let's see, I would have to multiply both sides by 0.024. Seems like it's time to change colors. Just interesting. And would you agree that I don't really need to multiply it by C? Again, it might be good form to kind of call that C1 so that you recognize those aren't the same C's, but 0.024 times a constant is still just another constant. It's a different constant than it would have been before. And then of course, now to get rid of natural log, aren't you going to raise both sides to the E power? Hey, that's looking good, isn't it? Didn't we have that on there? And then I could say plus C up here, which would be true. Or I could say, as it makes more sense to say, times E to the C, since you're adding exponents. And again, I find myself wanting to, call this C2 and then just rewrite this whole thing as C, because E to the C is still just a constant, right? And it's an ugly constant. So why not just replace it with a normal constant? And so then we're done. If I take 4.8 and I subtract all of that C business over to this side, and I add the 0.024i to the other side, notice when I divide by 0.024i, I get the same answer. 4.8 divided by 0.024, we said earlier, was 120. Notice I get C divided by 0.024, but the E kind of really doesn't change. And so again, I could rename this C value even a fourth time now. If I went kind of back and said, I guess this was our third constant, then I'm going to rewrite all of this as kind of our fourth constant. That was our third constant. So now that looks exactly like what we had before. So that's just kind of cool to see. You don't need to know that. On a test, if I didn't say, if I just said answer the question, then you'd be free to do this either way. I think you would agree with me that actually the linear way was easier. I mean, it requires more knowledge, but that's just kind of cool to see that that's the same answer. I want to ask just kind of another separate question that pertains to this. What if the output rate wasn't 12, but it was actually less, say 10 gallons per minute? Now notice if you have 12, and again, that's liquid, you have 12 coming in and only 10 going out. Does it make sense you're gaining 2 gallons a minute in the tank? Now you might say, if that's a tank, that isn't going to work because tanks are enclosed. But if it was a lake, it would work. Right now the lake is actually filling up, and that's super common with lakes. Like if it's a dammed lake, they'll let maybe more out than comes in for the sake of fish, or maybe because they're saving the water for summer, they'll let less out than actually is coming in because they're trying to fill the tank up. And so I want to give you a second to think about that. Could you rewrite this? Could you rewrite this differential equation if the output rate is different than the input rate? Still di dt. The rate in is still 4.8. But what's the rate out going to be?
You're just going to multiply by 10 instead of, I think we did 12 initially, right?
Yeah, it's not terrible. I'll bring this back up so you can see this. So yeah, in a sense, all that's really going to change is this statement right here. It's still going to be I over 500, but then this is a 10. What I just said is kind of true, but actually not completely true. What do you think about that?
And you have to, like, this 500 still hold true.
Yeah, because notice if you didn't think about that, 500 doesn't still hold true because is the tank always have 500 gallons in it? No. No, it doesn't always have 500 gallons in it.
So would it be like 500 plus 2x or 2t, I guess?
I'll let that hang for a second. So it sounds like Connor's voice. Connor's saying, would it be 500 plus 2T? Where'd you get 2?
You got that extra 2 gallons a minute that are being added to it.
Yeah, because you got 12 coming in and 10 going out. You're actually gaining. You're gaining, not losing. Gaining 2 gallons a minute. So that 500 is not 500 either.
Would it be 500 minus the amount that you're, or added to the amount that like you're gaining based on the rate?
Yeah, so for our problem to ultimately lay the question to rest, this is going to be a 10 now. But that 500 isn't going to stay 500. And Connor was exactly right. It's 500 plus 2 gallons per minute. So I'd have to multiply 2 gallons per minute times T minutes so that you end up with 2 times T. So you're gaining, that's why there's a plus sign, you're gaining 2 gallons every minute. And so there's a T involved in that. It's not just 500 plus 2.
Are we stating then that our initial condition is at 500 gallons?
Yeah, so notice that becomes part of the initial condition too, that it started with 500 gallons in it. So it started with 500 gallons and it started with 50 ounces of iodine. But now the liquid in the tank and notice that kind of screws up the concentration question too. But notice this is a much more interesting differential equation now, because now there's suddenly a T in it. And so do you find yourself going, uh-oh, I don't know how to solve this now. It's amazing that tiny switch, what difference that makes. I want to give you a little time to think about this. I want you to also think, is this still separable? Can I separate this now? If I wanted to, could I solve it as a separable differential equation? Do I have to solve it? Is it linear? You see what I'm saying? Like, we're not that good at this yet, right? If I just say solve this, it's kind of like, I'm not really sure what to do now. It's not so obvious. Well, I don't want to belabor the point too much. I'm going to think of it as a linear for now. I'm actually not sure if I could separate this. I got to think about this a little bit more, but and you should also notice you can't separate, or you can't simplify 10 over 500 because it's also being divided by 2. Now you could divide the top and the bottom by 2 if you wanted to. And that could actually make your life easier. In other words, it'd be 5 over 250 plus T. That actually might make your life easier. I think I'm going to not do it just for the fun of it. Do you understand why I rewrote it with the I not kind of up there with 10? The reason I did that is because I need to collectively look at this entire junk right here and say that is kind of my P. That's what I need to know to go mu hunting, we said yesterday. So this is going to be a much nastier integral, right? Or a much nastier problem. What is the, so we say mu is found by taking e to the integral of, and now that isn't just a constant. So we're suffering vastly. So I think, whoo, that's a dangerous integral. And because I'm a little worried that I can't do this by way of a shortcut, I am going to make a substitution here and let u be equal to that denominator, which means du is the same as 2 dt. So that means my integral statement that used to be 10 over 500 plus 2t dt is now 10 over only u, which is really wonderful. But then I got to replace that dt, and notice that dt is equal to du over 2, because I got to move that 2 over. So now I basically have 5 over u, the integral of 5 over u. Oh, that's easy. That's 5 natural log of u. And replacing it, that means mu is equal to e to the 5 natural log of u, or actually 5 natural log of what u was equal to, which is 500 plus 2t. Again, that isn't from yesterday. That's an extremely ugly value for mu. But you should understand that that is the same as e raised to the natural log, since that 5 can pop up top and be natural log of that same junk to the 5th, then that means e to the natural log, those cancel each other out. And so the mu is actually just 500 plus 2t to the 5th power. So there's my multiplier. Wow, that was complicated. So again, as I mentioned yesterday, I find myself thinking, really? Does that work? I can't believe that works. Let's find out. Notice if I multiply this p-value times 500 plus 2t to the 5th, well, there's 5 on the top, 1 on the bottom. Do you agree that that actually cancels one of them? And so now I only have 500 plus 2t to the 4th. You agree with that? And the 4.8 also gets multiplied by 500 plus 2t to the 5th. So, oops. So the question is, does that really work? Is that really the power rule right there? And of course, the question there is if I took the derivative of 500 plus 2t to the 5th, would I actually get this? So I think, okay, well, 5 comes down front, chain rule. The outer function is junk to the 5th. So the 5 comes down front. I look over here and I say, oh, there's no 5 out front, but there is a 10. And then this goes down by 1. So that becomes a 4. So there's a 5 sitting out here, but then times the derivative of the junk. Oh, the derivative of the junk is 2. So 2 times 5 is 10. Wow, that actually worked. I can't believe it. That's amazing. So sure enough, that's actually the power rule sitting there. So that means I can proceed and rewrite this as 500 plus 2t to the 5th times I. Again, the non-derivative portions of this. The 10, 500 plus 2t to the 4th is a derivative. The di dt is a derivative. So the non-derivative versions. So I rewrite it as the power rule before it had been taken. And now I need to integrate both sides. In the interest of time, I'm going to do this a little less formally and kind of get it done a little faster. So 500 plus 2t to the fifth times I equals the integral of that side. The integral of junk is raise the power of the junk up to 6 and then divide by 6. But I'm not quite done. What's missing? Screwed up the chain rule.
Multiply by 2. Oh no, divide by 2 because of that 2t in there.
Yeah, divided by the derivative of what's inside. The derivative of what's inside is 2. If it was a derivative, I'd be multiplying, but because it's an integral, I'm dividing. Again, it would be much safer to let u be 500 plus 2t, and then you wouldn't have to be guessing. So you don't want to do what I'm doing unless you're kind of an expert at this. And so, great. I'm home free. And of course, there's a plus c, which is really important because my next move is going to be to divide both sides by this statement right here. I'm going to divide that away from both sides. Notice in the first part of this problem, you end up with 4.8 divided by 12, which I'm inclined to want to turn into a decimal, and I got 0.4. And when I divide by 500 plus 2t to the fifth, the fact that there were 6 of them here means there's only going to be 1 of them left. Isn't that interesting? But the c value will be divided by all of them, which I'm choosing to move to the top and make -5. Is that a good idea? I don't know. And since I of 0 is equal to 50, let's see if we can even make the equation precisely correct. So I is a function of t equals. This is kind of interesting. I got the same 200 again. Then I also got 0.4 times 2t, which is 0.8t. But I'm putting in t is 0 for that. And then plus c times 500 plus 2t. But t is 0, so these two terms are going away. And I is 50. So I have 50 equals 200. Not 500. 50 equals 200 plus c times just 500 to the 5th power. Wow, that's a gigantic number. So what does that mean?
Negative fifth power.
-5th. So thank you. So I think I'll write that just so that it looks a little better. Thank you for catching that, because that would have been fatal. That 500 to the 5th is actually on the bottom. So I'm subtracting 200 from 50, that's -150. And then I'm multiplying that times 500 to the 5th power. That just seems like it's really going to be enormous. So it's such an enormous number, I kind of find myself thinking I can't even write it down. So I guess I'll say c is equal to -150 divided by 500 to the 5th. Maybe I could simplify that a little bit, but let's just leave it alone.
Wait, wouldn't it be -50 times 500 to the 5th? Am I thinking of that wrong?
Times, yeah, I said times, but then I wrote divide. Thank you for catching that. Yeah, so I got the number -4.68 times 10 to the 15th, meaning there's a lot of zeros on that number. Thank you for catching that, because yeah, I'd be multiplying. Doesn't that feel just kind of astronomically large, almost like, can this really be right?
Well, it's astronomically small, isn't it? So 200 plus 0.8 T is actually like the real meat of the equation.
Yeah, notice when t goes to infinity, this is a side point, but when t goes to infinity, this term is going to go to 0 because this is going to be 500 plus infinity, but it's moved to the bottom. So although 500 to the 5th power is a big number, 500 to the infinity is a much bigger number. This whole thing is on its way to 0. So basically this whole equation is going to act like the line 200 plus 0.8 t. Well, at least when t gets really large. So let's go look at our differential equation. This is what I'm going to type in to our cheat slope field. Except again, I got to be careful because it's y's and x's over there and I've got i's and t's. And so I got to think a little about this. Let's go look at that. Again, what we're doing now is checking our work / sense making. Sense making is extremely important. So it was still 4.8, still minus, but now it's 10i, which for us would be 10y divided by parentheses again, 500 plus 2t, which for us would be 500 plus 2x. So I'm looking down here to see if what I typed in is actually right. 4.8 minus 10 times y, or yeah, looks good. What do you notice about our new direction field? What do you notice that you're maybe not surprised by? Does it now limit itself at 200? No, notice it doesn't, and that should make sense to you because it's what it's going to limit itself to is 0.4 ounces per gallon, right? But the number of gallons in the tank is going up. So 0.4 ounces per gallon multiplied by lots of gallons is lots of iodine. I can't add this to the graph, but can you picture if I zoom out far enough based on what I said earlier, that if I was able to graph the line y equals 200 plus 0.8 t, that these would be lying against it asymptotically out there. By the way, this has to do with tomorrow's project. In other words, there's an asymptote here that I can't see. I'm going to take these out to, this is probably way too large, but it seems easy. So I'm going to take them out to 4,000. Maybe it won't even like that. Notice I didn't need to take it quite that far. Do you see how they're all, notice how that actually looks? So you can't verify that it's correct because I don't have any way to graph it. But notice that's on its way. They all behave the same. They're exiting the stage according to an asymptotic line. That's kind of cool, isn't it? Since the C part of that went to 0 as t goes to infinity. That's really cool. So it's a very different model now. Isn't that kind of neat? And of course, if I go into our initial condition, which was 0.50, we won't take the time to do the algebra here, but does it make sense the solving for t here? If we had some reason to stop at 120, like I don't really care how many gallons of liquid are in the tank. I want to stop at 120. That'd be harder to solve. But it'd be even more interesting if we actually stopped at a concentration. Do you agree with that? I don't care how much is in the tank. I just want it to be concentrated a certain amount. Isn't that kind of interesting? So I'm going to turn the tank off. Well, let's see. The original was 120 divided by 500, which we said was 24%. So what if I wanted to turn this off at 24%? I want to turn the pump on and turn it off when the concentration's at 24%. And I don't really care. And this would be the way it would be for a lake, right? Like I don't care how much water's in it. I just want it to be healthy or whatever that means. And so what would that look like? I'm asking really hard questions here, harder questions that are going to be on the test and so forth. But I'm asking interesting questions, and that's kind of what I'm after right now. So we found our model. Since there is a concentration question in your assignment, it just makes me think we should play with this a little bit. So we have our model. Maybe we'll cheat and use Desmos to answer this because we can graph that in Desmos, right? So we don't necessarily have to do all the actual equation solving. But the question is, what does it mean to be 24% concentration?
Is that 24% of the volume is the substance?
Yeah, that's right. So if I took 24% times the volume, what's the volume though?
Are we still doing 500 plus 2T?
Yeah, it's 500 plus 2T. What is that equal to? Like, what is that?
It's equal to our I. That's our.
Exactly.
Differences.
That's your I. So then isn't that the equation I'm solving? If I took this expression right here and I stuck it in up there, then I'd be solving that equation for T. Isn't an equation that just has one T in it? And maybe that's easy to solve algebraically, but let's be a little more sophisticated. And maybe I don't know. Actually, I'm not sure. Like off the top of my head, is that a hard question algebraically? I don't know. I'm going to say this for extra credit. By the way, what I do with extra credit in my classes is if you do them and you end up close to a better grade, like say you ended up with 89% at the end of class and you're like, is there anything I can do to get an A? I will say, yeah, remember that extra credit on July 20th? Did you do it? And I'll look in the grade book. Oh, you did. You did some of those. That's cool. I mean, it kind of gives me an excuse to give you the benefit of the doubt. Again, I actually don't know the answer to this off the top of my head. Is this easy? Am I giving you a ridiculously easy algebra extra credit here? But would a person in the real world do this? No, because it's time consuming and dangerous. You've watched me make 3 or 4 mistakes today, right? You caught them all. But couldn't I solve this using Desmos? Let's go do that. I'm going to do it as a system of equations. I've got I equals one set of gobbledygook over here, and now I've got another one. I equals another set of gobbledygook. I want to see where they run into each other. Do you understand principles of algebra well enough to say, yeah, I just need to see where those 2 graphs hit each other? Wherever they hit each other, that's going to be the time and the iodine concentration, by the way. So we said new equation, 200 plus 0.8 T minus 150 times 500 raised to the 5th times 500 plus 2T. Actually, maybe I'll write it this way instead. I'll say divided by 500 plus 2t raised to the 5th power. Since it was a negative, I'll just write it on the bottom. It's kind of what I might need to do to solve it anyway. Maybe I'd need to write it that way anyway. And then our second equation was 0.24 times 500 plus 2t. So I do want to show you something quickly over here. Notice over time, does this asymptotically lay against the equation 200 plus 0.8t? Notice, yeah, isn't that cool? It exits the stage along that asymptotic line. So that's kind of cool to think about. But what we're interested in is just, where do these run into each other? Again, isn't this both time consuming and foolproof? Well, foolproof if I double check to make sure I typed it all in right. And Desmos is really intuitive in the sense that it just lets me click on that point because it kind of knows that's an interesting part of this. And so notice the answer is 27 minutes. And not only that, you'll have 133. I want you to play with this for a second. Can you check all of that? If you went for 27.6 minutes and you had 133.24 ounces of iodine, remember that's the meaning of X and Y here, T and I, would that actually be the correct concentration? Can you prove that that's 24%? So you should say, I gave you enough time to at least take a stab at it. You should say, well, the concentration is 27.613 ounces of iodine. No, that's time. 133 is that. But how many gallons are in the tank? Well, didn't we say the equation for that was 500 plus 2 times the time, which we now just figured out is 27.613. So if I actually divide those, I'm hoping I will get ounces of iodine per gallon. I'm hoping I'll get 24% or darn close to it. If I don't, then something's wrong. Maybe my check is wrong. Maybe something I did is wrong. I don't know, but 254 divided by, since I use Desmos to sort of cheat and do all of this, I'm very confident, I guess you could say. Yeah, I got 23.9999% or something like that. So yeah, that is approximately 24%. Check. That's kind of cool. But it's crazy when that's involved, isn't it? Now, we won't take the time to do this, but another question I could ask is a third question about the same exact tank is, what if it wasn't 12 going out of the tank or even 10 going out of the tank, but what if it was 14 going out of the tank? In other words, the tank was losing 2 gallons a minute. Well, notice if it's 2 gallons a minute and it started at 500 gallons in 250 minutes, there's going to be no water left in the tank. Isn't that kind of interesting? Just because I think this is really easy to do, I think I can show you what this would look like. Isn't this going to just change this to a minus sign? And that 10 is now a 14. Is that it? Is that everything? Is that all I would have to change? 14 gallons per minute go out. I think it is. Does this graph make sense? Notice, sure enough, at 250, there's no more iodine in the tank. What's particularly fun about this question is, notice it started at 50 and it increased for a while, but we were also losing water for a while. So notice there's a super interesting calculus question here, which is what time is the amount of iodine in the tank maximized? Because that actually goes up for a while and then actually goes back down, and then there's none in the tank because there's no liquid in the tank at all at 250 minutes. So that's pretty interesting question. Notice it appears that that happens at 60 minutes or right around 60 minutes, just cheating off the graph. But that's kind of fun too, isn't it? So there's just a lot of interesting questions. And so, you know, again, that's kind of a dumb example in a tank, but if you have a river flowing into a lake, and I was just at Applegate Lake, I tried out some paddle boards yesterday. It was kind of fun. That lake was super low, you know, and so right now there's not much going into the lake, but they're letting more of it out because there's fish and recreation downstream. And so they're letting more of it out, and also irrigation and so forth. So that thing is actually going down, 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 down. If we let it go forever, there'd be no water left in the tank. But of course, there's enough time that, you know, winter will come, it'll rain, it'll fill back up again. But that's pretty practical. So, but just notice how much that adds to the problem. I'll give another extra credit question here. Could you actually mathematically, since you know how to find maximums, you take derivatives of stuff and set it equal to 0. This feels like a much harder extra credit question. Could you actually mathematically find that maximum point up there? Is there a way to locate that? Seems like a cool question.
You'd be looking for the tangent line, right?
Yep.
When it's 0.
So you'd have to find the equation for I, solve it yourself, find the equation for I, and then you'd have to take its derivative and set it equal to 0. Now there's a part of me that says, well, wait, don't you already have the derivative right here? Isn't that the derivative right now? So there's a part of me that thinks maybe I could shortcut that process, but that's very interesting to me. But, you know, I have to be careful as a teacher because I don't want to make this too hard, and I want to help, you know, prepare you for your assignment. And I still need to do some preparing for your assignment. So I guess I'll just leave that in the land of extra credit. Which pains me to do because I find it an interesting question. The heartbeat of math is asking and answering interesting questions, not just doing boring book problems. Share screen. So I do want to spend the rest of our little amount of time here just kind of giving you a few hints about some questions in the assignment, because there are some tricky things in the assignment. So I guess I'm just gonna have to be really specific since we don't have a lot of time. I've already kind of answered this question, but there's one more topic that's discussed in this section, and it's the Malthusian, I've never used this word with you before, but the Malthusian model.
I was going to ask if we were going to do the logistic function.
Yes. The Malthusian population model, put into words, is that the amount, the change in a population is proportionate to the population. That's the way you'd put it into words. And what this is just a percent. It's like if you said, and we've done examples of this, if you said the population is increasing at 6%, well, then you would say dp dt is equal to 0.06 times the population. Like that would be the Malthusian model for population growth. So that's not a hard differential equation to solve. Ultimately, the 0.06, you know, when in the beginning, this is just a K. A lot of times it's K stands for a percentage, whereas C stands for a constant. So that could be anything. It could be -6%. It's going down. And so the change of the population is proportionate to the population. Do you see that in this pithy little statement? Is equals change of population proportionate to the population just means these two things are equal. Well, they'd be equal if you multiplied one of them by a constant. That's what proportionate means. Or you could even think of it as dp dt divided by p is some constant. That's the way you think of something being proportionate. But there's a question that deals with that. There's also a wonderful question about a snowball melting or something. I haven't looked at this in a while, but let me take a quick look at that. It's question 22, I think. Just want to give you a hint about that. Let's read it really quickly. I don't want to give too much away because it's kind of fun to have to think about things a little bit, but I don't want to suffer too much. So it says, surface, this is a great question. The surface. Suppose the snowball melts so that the rate of change of its diameter is proportional to its surface area. That actually kind of makes sense that it would do that. Let's stop and think about this, because surface area is a big part of biology, because an animal exposed to the environment, how much surface area it has will determine, how sunburnt it gets if it's a person, or how much water evaporates off your skin will be proportionate to how much skin you actually have. And so the question is, could you write that statement down? And I don't know if I'm going to answer it, but it says it melts so that, and the snowball is a sphere, so there's a little bit of geometry here. You should know some algebra formulas about the geometry of a sphere. What's its surface area? What's its volume? But the snowball melts so that the rate of change of its diameter. Can you write that statement down? How do you write down the rate of change of the diameter of a snowball? You should think in terms of what I just wrote a second ago. And then they say it is proportional to the surface area. Can you see what I just said being the same statement? So what did I say up here? The rate of change of the population is proportional, that's the K, to the population itself. We're saying the rate of change of the diameter is proportional to the surface area. 22 is a pretty challenging question. I don't think give any more of that away. But this is a wonderful differential equation question, just because, it can sound playful if you're like, hey, my snowball's melting, but if you think of it in terms of biology, and like a cell inside your body is responding through osmosis, sending liquid through the walls of your cell, and you're made of many cells. And if this isn't working right, you're dying very fast. And so its ability to send liquid, salty liquid, through the cell wall would be kind of proportionate to the surface area of that cell wall, because the cell wall is resisting the flow of liquid through it. And so surface area is a big part of kind of how nature works. So this 22 is a really interesting question on a larger level. So again, as always, you're more than welcome to ask me tomorrow, because you owe me your homework, I think, tomorrow. Is that right? Which gives me time to give you the solutions to that assignment, so you can kind of look at them a little bit, my solutions, not just the answer, but how I arrived at my answer, in case that helps for the test. I consider 22 a tricky enough type of question. That's not the kind of thing I'm going to put on a test, but you have time to get an answer and say, hey, did I get this right tomorrow? That might be what we start class with. Cool. Let's see. Yeah. Guess we'll have to call it good. I wanted to do kind of another tank problem, but we certainly don't have time for that. All right, I guess we'll be done. As I said, tomorrow I'll be posting a project. I think the project is already posted. You could actually look at it before tomorrow if you wanted, but we'll be messing with that / the test. And for the most part, what I'm going to do on a lot of those days is introduce the project, and then you kind of have the rest of the time to be working. You can work with other people. You can be asking me, you can be working on the test review while you have access to me to answer questions. You can be working on the project. The project will be due a few days later. In a sense, I'm giving him those to you so that you have, in this case, you have over the weekend to kind of work on that, so you can kind of put the project off. But cool.
Where can we find the project?
It is, let's go have a look.
Yeah, it just looked like, I don't think it's up.
Maybe
The spot to turn it in is visible, but I can't see it.
Oh, maybe I set it so it wouldn't actually pop up until tomorrow. Let me look right now.
Actually, I'm able to see it. The PDF showed up once I actually clicked on that.
Yeah, I feel like I opened it up before.
Yeah, you should. I thought you could. Yeah, it's in there.
It's in the turn in place.
Oh, I gotta click start. Okay.
Yeah. So I'll elaborate that tomorrow, but those are actually all open now. Like you could look at any of the projects right now, but they're not time sensitive. I mean, I have a due date on them. That one is due Sunday night, so that you have time, to start Monday with something else. So it's not due till Sunday night, but you can actually open those early.
Just be careful. I think when you open them, your grade book gets a little like
Correct.
weirded out.
Yeah, because then it's going to look like, as soon as you open it, the grade book will say you have 0 on it now, and then you'll look like you're doing terrible. But we don't have much in the grade book right now. As soon as I get your assignments graded, you have one thing in there. But yeah, don't worry about that because it'll look weird for a while.
It's cool if we work together on the projects. Yeah.
Yeah, and I want you to understand my philosophy in these projects are, I want every single person to get 100% on them because they're neat. And I want you to learn from them. They are not like, gee, I need something to stick in the grade book, because they're a pain in my neck because I've got to grade them. I do them because I want you to learn from them. So, getting a C on it defeats the entire purpose of it, which basically means I want you to work with other people. I want you to ask me questions. I want you to say, hey, I don't even know where to start. Can you give me a hint? Like, those are okay kinds of questions. I want you to, do as much as you can under your own power, because it feels really good. Like, hey, I got that entirely by myself. That feels awesome. I mean, anytime you can do that. But I've got some hard projects in this class, and they're going to, take some teaching on my part for you to even start them. This is a less complicated one than other ones. But I'll introduce that tomorrow. But
Yeah, I'm gonna be in the Discord this weekend working on it then.
mm-hmm. Yeah, and sometimes I'll say, you can work with other people, but you have to turn your own in, or I might just say work with. I don't want you to work with 10 people and just have your name on it and you did nothing. But if you work with 3 other people, you can give me one project and it just has everybody's name on it. That's okay too. So you're all just discussing it, talking about it. And again, that's because I want everybody to leave understanding it. Obviously in a group, there's going to be one person that maybe carries it a little bit more than other people. And that's okay. It's like some people are more gifted, or maybe it's more interesting to them. They spend more time on it. But they're learning opportunities to me. Cool problems that don't fit in the everyday sequence is kind of what it comes down to. All right, get out of here or stay after. I will see you tomorrow.
Thanks, Doug.
So,
You all.
I was wondering if anyone had a question. I was just going to stay and listen.
Yeah, stay and jump in.
I have a question about homework that's a little bit ahead of time. If somebody else wants to go first on something more relevant.
Well handled, David. That's fair.
I'm still gathering my stuff, so you can go ahead.
Okay, well, let me quickly pull up the homework scheme. So it's from 4.3, and I just got an interesting solution that I felt a little too easy. Or actually, well, it felt unrelated because it's when we start doing complex numbers, and I just didn't get
Yeah.
it was just really a simple answer. Anyway, so it was 22 on 4.3.
Okay.
And I ended up getting a weird, one of my constants here. I can just ask you, one of my constants turned out to be 0. Can that happen?
Yes.
Okay, so that's okay.
Yeah. Mhm.
Okay. Well, I kind of just got weirded out because I figured, I don't know. I just figured I'd ask.
Yeah.
So
No,
I
that's
guess that is a particular solution then. And so it
Yeah.
could, okay, so it's, okay. Yeah, I
Yeah,
guess
and-
it makes
and-
more sense.
you got to look at 0 as just one of the many numbers we have, and it's just as likely or unlikely to come up as any other number. And so generally speaking, in a book, that might come up only because somebody worked really hard to kind of try to keep the answer simple or something. But yeah, I'm looking at my solutions and I got 0 for one of those constants. So
Okay.
that's a good sign actually that maybe you got it right.
And I actually, let me see. I was wondering if I could check some of my solutions for 3.2.
Sure.
I think after what we did today, I need to go back and redo at least one of them because I didn't, I screwed up with the changing volume.
That's not easy, is it?
Yeah, I just didn't, it didn't occur to me.
Yeah, that's not obvious. It's surprisingly complicated. So yeah, fire away. Any questions you want to check? Go for it.
Okay, well, like for number 6, should I just tell you what I got?
Yeah.
For the time, I got 8.44 minutes.
That's not enough.
That's not an, that's okay. That's too little.
Yeah,
Okay.
significantly too little.
Okay, I'll redo that one. That looks like it was another one that I could probably redo. Oh, sorry, one sec. My alarm's going off. And then for number 8, I got 1/2 for the
That is
limiting
correct.
time. Okay, that's correct.
Mhm.
For 14, I got 12,657.
That's probably rounding, but yes, I'd say so.
Okay, so I can be more, okay.
Well, yours could be better than mine. I rounded and you rounded. We each had our own way of rounding. So yours could actually be right. Mine's wrong, but I think I don't care about rounding. So as long as your work sort of leads to your answer, then great.
Yeah, I left it exact until the very last minute. So
Got
I
it.
don't
So
know.
yours is probably more right than mine, but we're both accurate to the hundreds place. So that means you're certainly right.
Take that, Doug. Okay, and then for 24, I got 41.94 years. 41.94, did I say? Yeah. And I was a little unsure about that one.
Which question did you say? Number what? One more time. 20 what?
24.
4.
I got 41.94 years.
Did I sign 24? I don't think I signed 24. You mean 14? No, I don't know.
Wait, what, did you not assign 24?
In 3.2?
Yeah,
Check. No.
you didn't? Oh, okay. Well, what was there one that came after 14?
22. That was the one I was hinting at about the snowball today.
Oh, that's weird. I must have made a mistake. Okay, well then I'll just I'll write 22 in there. I thought it was just an extra problem. Maybe, you know what, did you change it perhaps? Because I'm still, the syllabus that I downloaded was the one you did before you changed.
I didn't change that. I did change a few things. I got rid of section 1.1 but I know I didn't change that because I've made the solutions to these, the first time I taught this class, and I didn't change that one, I know. So I don't know.
You know what, you're right. It is 22. I wonder where I got 24.
Not hard to do.
Well, okay, well, cool. And I'll, what is that problem? Is that like, is it 20?
That's the one where the snowball is melting.
Oh no, I know. I'm looking at what's 24.
Oh,
Okay,
gotcha.
so it says if initially there are 300 grams of a radioactive substance and after 5 years there are 200 grams remaining. So would I just say that it decreases proportionally to the amount of substance remaining? So it would be EX.
That's exactly right. That's a Malthusian model type of an equation.
Nice.
And it's half-life, yeah.
Right. Well, they mentioned half-life in the instructions above, But then I
Mhm.
didn't have to do anything with half-life in that problem, so I was just a little bit uncertain. Well, okay. Well, I'm glad I checked.
I think you do need to use that half-life. I'm not sure about that. If there's a substance is the time.
I think you have to use it for the next problem because the next problem mentions the half-life.
Yeah, I think you're right. I think you're correct. I don't think you do need it for that question. You're exactly right.
Okay, all right. Well, otherwise, all of my questions are a little bit ahead of time, so I will just wait because you might answer it.
Fair enough. Good job.
Have a good day.
You as well.
I just had 2 questions about stuff from 2.2, and I can share my screen. Okay, I think part of my trouble is just taking these integrals that we haven't really, these ugly integrals, but I'm also
Mhm.
not sure if I'm on the right